All right, friends, here goes nothing. I'm going to try and teach this as if we were in class, and we'll see how it goes. So this is the next unit. It's called Applications of Forces, Chapter 4. As we go, I'm going to show the notes here, and then I'm not going to leave them super long, so that's what your pause button is for. So for example, this right here, this is your next page of notes. This is the first lesson. So this is for the unit. That's the unit, but this is the first lesson, gravity near the Earth. So what I'm going to get you to do is pause it so you can write this stuff down, and then I'm going to talk about it. So you pause it now, and you've unpaused it. All right, gravity is stronger near the center of the Earth. So center of any body, there's gravity associated with any body, and it is always based kind of on the center. Weaker on Mount Everest or at the equator versus the North Poles, but not enough for you to notice. It's like the gravity amongst other bodies. There is a gravitational pull when you pass somebody else in the hall, but it's tiny, 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 tiny. Non-contact force drawn with vectors pointing to the center of the Earth. Gravitational field strength is the force per kilogram of mass acting on an object. In this case, it's 9.8 newtons per kilogram. And if you think about that, force equals mass times acceleration, or mass times gravity. Force divided by mass, that's your 9.8. So it's newtons per kilogram down, which is also meters per second squared. The gravitational field strength at a location has the same magnitude as the acceleration due to gravity at that location. Cool, cool, cool. All right, next page. Mass versus weight. Mass is the amount of matter in an object. Weight is the measure of the force of gravity. That's an important distinction. Mass and weight are different. Weight is a vector, mass is not. This is in kilograms. Weight is in newtons. Weight is the measure of the force. Oh, I forgot to tell you to pause this and write it down. Whatever, maybe I'll talk about it first and then you can pause it. You can pause it whenever you want. You're in control here. You can mute it if you want. Your weight changes from here to the moon. Your mass doesn't. Astronauts aren't weightless. They're actually in free fall. Okay, feel like I'm waiting for you to write it down. Don't need to wait. Slide 4. This is all still first unit, or first lesson. Air resistance and free fall. I'll let you pause it here if you want. All right, air resistance is friction caused by air. The faster an object is falling, the more air resistance there is. Think of it, it might be easier if you think about water. It's hard to think about air, but if you're in the water, you're going to get more resistance the faster you are going. That's why, if you're water skiing or something, the faster you go, the harder you hit, the more resistance. Also depends on cross-sectional area. Think of it as a footprint. Compare a sheet of paper with a crumpled ball of paper. The sheet of paper has more cross-sectional area. This is also why a bowling ball falls faster than a feather. Remember that video that I showed you guys? It's because of air resistance. With no air resistance, they fall at the same time. Any object is said to be in free fall when gravity is the only force acting on the object. Consider figures 2 and 3 from pages 162 and 163. Let's you look at those. Last one here. Read tutorial 1. In problem 2, simply add the acceleration first instead of doing twice the work as the example shows. So for those of you, I know some of you skip the tutorials. I don't recommend anybody does, but I'm guessing that some of you do. So those of you that don't, and you shouldn't, follow this note. This is your assignment. I'm going to do these practice questions with you in a couple seconds. With you, for you. Okay, so this is going to be the next day, so I'm going to leave it here, and hopefully I don't lose this or misplace this. I might as well just keep it one big long recording. Sorry for the dead air. It's the first time I'm doing it like this, all right? Give me a break, man. All right. We'll zoom in a little. Let's try this bad boy. Okay, so this is page 166, practice 1A. Says, that looks like page, it's 1A. A 12 kilogram box sits on top of a 38 kilogram box. Draw a free body diagram for each box. So this is the 12 kilogram for each one. So we're doing this separate. I know this is sitting on top. This is the 38 kilogram. This is the force of gravity. This is the normal force. On this, it has the force of gravity. You'd also say there's an applied force because of that box sitting on top of it. And then it's got the normal force is pushing up. The normal force here is going to be countering both of these, right? So these two together are going to equal that one. Is that clear? I'm just looking at the screen now. I think that's probably okay, hopefully. Maybe I should use a marker. Alright, let's try it with a marker. Calculate the normal force acting on the 12 kilogram box. So this is 1B. Normal force, mass times acceleration. So the mass is 12. Acceleration is 9.8. Times 9.8 is 117.6. 2 sig figs, so that's 120 newtons up. Direction is important. Calculate the normal force acting on the 38 kilogram box. So that's 1C. Same idea, Fn equals m times a, except in this case the mass is 12 plus 38, so that's 40, that's 50, so it's 50 times 9.8. My phone's in the way. 50 times 9.8 equals 490. Look at that, sig figs and everything. 490 newtons, and that is up as well. Hopefully that makes sense. Man, this is going to be a long video. It's weird talking to myself. I guess I keep going quick, but if it's too fast, you can pause it, right? Please send me questions, respond to this, or iMessage or email if you have questions. All right. Number 2. Question number 2 says, a child has a mass of 36 kilograms, okay, m of the child equals 36, and is sitting on a seat on an amusement park ride. The ride makes the seat move up and down. Of course it does. Determine the normal force acting on the child when the child is moving. So A, moving at a constant velocity of 12 meters per second. Constant velocity means there's no outside acceleration. It's just gravity. So F equals mg, which is 36 times 9.8. I need to get a different calculator. I don't like using my phone. 36 times 9.8 is 352.8. In sig figs, that's 360 newtons up. Oh wait, 360, that's poor rounding. 350. 350 newtons up. For B, moving down at a constant velocity. It's another constant velocity question. There's no additional acceleration. When I say additional, it could be adding a positive or adding a negative. So it's still going to be 350 newtons. You're going to get questions like this, this year and next year. When acceleration is 0, then you just have gravity to worry about. And that happens with a constant velocity. Part C says accelerating down at 1.8 meters per second squared. Okay, so if it's accelerating down, think of it this way. Maybe I'll turn the page. So for part C, we know that acceleration of this ride is 1.8 meters per second squared down. Now think of this. You might want to add 1.8 to 9.8, but don't. It's kind of like if you're in an elevator and it's accelerating down, it feels like you kind of float for a little bit. You kind of rise up a little bit before you drop. Do you know what I mean? So the actual force then is less. Think of the force on your feet standing in the elevator. When the elevator goes down fast, like hospital elevators, you kind of feel that in your stomach. You're feeling a bit lighter. So our net acceleration is going to be 9.8 minus 1.8. So it's going to be 8 meters per second squared down. That is going to be your net acceleration. If you go up in the elevator, sometimes your knees buckle a little bit. And that's because there's more force. In that case, if it was going 1.8 meters per second squared up, then you would add it to the 9.8. So if F equals ma, the mass, what's the mass of this kid? 36 times 8. 36 times 8 is 288. Sig figs will be 290 newtons up, because we're still talking normal force. That's practice number 2. Pause it as you need. Rewind it as you need. For practice number 3, it says a 72 kilogram person jumps off a bathroom scale. 72, so their mass is 72. Gravity or acceleration normally is 9.8. Now it says the scale reads 840 newtons. Force equals 840. This is the force that the scale is reading, 840 newtons. Okay, a couple things to think of. First of all, normal circumstances, this 72 kilogram person, 72 times 9.8, 72 times 9.8, normally, standing on a scale, just standing there, 705.6 newtons. That is normal. We're told, when I say normal, I don't mean normal force, I mean they're just at rest, okay? We're told there's an 840 Newton measure. Why the discrepancy? 840 minus 705.6 equals 134.4. There's 134.4 Newton difference. This is what we're going to use to figure out that acceleration. So F equals ma, 134.4 equals 72a, divide both sides by 72. So it's 1.86 repeating. Sig figs 1.9 meters per second squared up. Yeah, this acceleration of the person, they are accelerating 1.9 meters per second squared up. That's them. This isn't kind of the net situation, right? This is them. So hopefully, sorry about that. I got to keep looking at the screen, making sure I'm seen. Let's do number 4. Four says, an electrician holds a 3.2 kilogram chandelier, mass equals 3.2, against the ceiling with a force of 53 newtons up. So the applied force is 53 newtons up. What is the normal force exerted by the ceiling on the chandelier? Something to consider here. The applied force, 53 newtons up. I don't know if a drawing will help. This is a chandelier. That looks like a person. This is supposed to be the roof. That's the ceiling. This is terrible. Somebody's holding it. That's their hand. And they're pushing it up. They're holding a small child by the neck up against the ceiling. This is terrible. Are those lights? Still looks like a person. Now they have mitts on. Anyways, They're pushing up with 53 newtons. Don't forget gravity is part of this situation. So they have to counter gravity. So think of it this way. What's gravity doing on this? Force equals 53, sorry, not 53. Force equals the mass, 3.2 times 9.8. So this is what gravity is doing. My phone went to sleep. I have to unlock it. 3.2 times 9.8 equals 31.36. 31.36 newtons. This is gravity. Okay? Doing this much. This is what gravity's doing. So the person who's holding this child up against the ceiling, they're exerting 53. 31.36 of that is gravity. If they were just exerting 31.36, the normal force from the ceiling would be 0. Okay, it would just be equal balance. So we need to find the difference, and that's what the ceiling is responsible for. 53 minus 31.36 equals 19.64. That is the force that the wait, did I do something wrong here? No, that looks right. That is the force that that's the extra force going into the ceiling. So this is the force coming down. So that's 20 newtons down. That's the normal force. Notice sig figs, I need to put that decimal there. I could put 2.0 times 10 to the 1 newtons down. Whoopsies. Make sure it's on camera. That's today's lesson. How does that look? That's what things are going to look like, I think, for the rest of this week, next week, and then the week after spring break. Okay, bye.